Hope I smash in the appropriate direction and not in the crash direction. So, first of all, thank you to the organizers for inviting me and allowing me to speak here. It really does feel like a great honor, so I really appreciate it. I'm very excited about this week as well. So, stability is in my talk, and there will be very little stability, though. So just a heads up about that. Okay, so I'm going to put this slide up here, so if you don't want to listen to my story, you could at least read what Safman had to say about vorticity. I actually came to this problem not through looking at stability. Bernard is going to be talking about what we call the pressure problem later today. And some researchers came to us and said, could you repeat this for the case where you have, let's say, constant vorticity? And we thought about it, and sure, we believe we can repeat this work for constant vorticity. So we started calculating traveling wave solutions, and everything seemed to be working out nice. And then as I was playing around with the bifurcation diagrams of these traveling wave solutions, I kind of got a little puzzled. The bifurcation diagram seemed to switch directions. I didn't understand why, so I figured maybe I should just look at the spectral stability. And that's what got me into looking at this project. I should acknowledge my collaborators. So Patrick Springer, he was an undergraduate. He just graduated this quarter, I guess in June, and he'll be headed off to CU Boulder for his PhD. And Vishal Vasant, who's a postdoc at Penn State, working in Diane Henderson's lab. So they're my collaborators on this project. So a little bit of motivation in terms of pictures. I like pictures. So we've all seen these sorts of waves that perhaps could be described by constant vorticity, this sort of rounded effect where you have waves coming into shore, and then you also have a flow going against the direction, and you get this sort of bulbous traveling wave. Now, there has been a lot of computation done in terms of traveling wave solutions with constant vorticity. One of them is Da Silva and Peregrine's paper, where they compute the bifurcation branches for various values of the constant vorticity. And they show traveling wave solutions that look kind of cosine-like we expect, but then you can get these overhanging waves. And it seems that with the right kind of vorticity that's large enough, these amplitudes seem to grow forever. So again, we were looking at redoing the pressure calculations that Bernard will talk about in regimes such as these. So, okay, this is the picture I like to look at when I think about constant vorticity. So one way to think about constant vorticity is inducing a linear shear on the flow, and we can have different configurations. If I imagine that I want to look for traveling wave solutions going in the positive x direction, then I could have a current which has a linear profile like such, and I extend the lines here beyond the domain for reasons that help me think about the problem computationally. There are three configurations that we can think about. One where the horizontal velocity minus the speed of propagation is always going to be positive or negative, as in case A and C. Or we could have a stagnation point inside the fluid domain, as you see here in the middle case. And this is something that we're going to have to think about as we do some of these computations. This is very different than the case where you have just pure gravity waves, where there are no stagnation points inside the fluid domain. You know that the horizontal velocity minus c is always going to have the same sign throughout the entire fluid domain. Okay, so this is a bit different. Okay, so I'm actually going to go through the equations of motion a little bit slower and kind of step through things a little bit. So that's a nice relaxing talk. Sit back, enjoy the show. I don't know. So we're going to step through these equations. And so inside the fluid, we're going to start with our typical equation, ux plus vz. U will be horizontal velocity, x will be the horizontal direction, v will be the vertical velocity, and z will be the vertical direction. So we have our equations inside the fluid domain, our conservation of mass, as well as our conservation of momentum equations, or our momentum equations here at the bottom. Here we have to consider the pressure P inside the fluid domain. So I'm not making any assumptions about irrotationality at this point. So we have our equations of motion inside the fluid domain. I'm going to be considering periodic boundary conditions, and just for easiness, the period is always going to be 2 pi here. Okay, there we go. At the bottom, of course, we want to make sure that our vertical velocity is 0, and I orient my coordinate system so the bottom is at z equals minus h. Some people put z equals 0, so just a note about that. Of course, my wave will be defined at z equals eta. And so at the surface, we have 2 boundary conditions. We, of course, have our kinematic boundary condition, and we have our pressure condition at the free surface. Here, I assume constant pressure along the free surface, and in fact, I'm just going to set that equal to 0. So the atmospheric pressure along the free surface is 0 everywhere. So if things try to pinch close, that's a different story. Okay. So in summary, here are all of my equations. Inside the fluid, I have my conservation mass, conservation momentum. I have my kinematic boundary conditions at the bottom, as well as the surface, and my pressure condition. Okay. Apparently, I like to be repetitive, so put it all again on another slide. I'm just going to skip past that. Now, we're looking for traveling wave solutions. So when I talk about traveling wave solutions, we're just looking for the free surface profile. And sort of, to me, the ideal situation would be to only have to solve for the free surface profile, not have to do any sort of discretization inside the fluid domain. So that's going to be the aim of the approach we talk about here. I move to a traveling coordinate frame, look for stationary solutions, and of course my equations just become exactly what you expect. Plug everything in, and just point out that everywhere I get a u, it can always be factored, so it's really u minus c. So that's going to be nice when we make some change of coordinates coming up in the next few slides. So again, this is just reformulating in a traveling coordinate frame. Okay, again, no assumptions at this point have been made on the vorticity, but now here's where we do this. So the vorticity, okay, is defined as the curl of the velocity field. For the 2-dimensional domain, 1-dimensional surface, this just simplifies to the scalar equation. Life's great. We're enjoying the equations. We're going to restrict omega to be constant. And one thing to note is that if omega is initially constant, it will remain constant for all time. It's an easy calculation to show. I think everyone had to do it in their first fluid dynamics class. Okay. So now we're dealing with constant vorticity. We're going to introduce the stream functions as opposed to the velocity potential, right, where psi z is, of course, my horizontal velocity, and the negative of psi x is my vertical velocity. Now it's just another change of coordinates, plug it in, boom, boom, boom. Our incompressibility condition, of course, just becomes the identity, whereas our vorticity equation becomes a Poisson equation. So our new equation here, that psi xx plus psi zz equals minus omega, that will replace our incompressibility condition. And now we keep going through all the associated boundary conditions as well as the momentum equations. Okay, so now we take a look at our momentum equations. Yay, total derivatives. We can integrate these two together and replace it with a Bernoulli-like equation. Here, capital C represents a constant of integration. I like to complete the square, so I've added an additional 1/2 c squared here, because again, we'll see these factors popping up. And of course, the rest of our boundary conditions follows, except for that one, which was looking a little bit ahead, because we're going to make another change of coordinates as well. So again, it's just sort of this stepping through. First, we go to the the stream function formulation, and then we're going to shift that, because what we really want here is something that looks more Laplace-like. Okay. So again, we make another change of variable. Bar phi is now going to be psi minus cz. And in our new coordinates, we end up with the following equations of motion. I've redefined f here in the form, instead of having that c plus 1/2 c squared term, I've redefined that as 1/2 f squared. And it's easy to show that that quantity should always be positive, so that this replacement is a matter of convenience. Okay. So now what I want to do is look at the boundary conditions at the surface and at the bottom. At the surface, or sorry, at the bottom, let's start there. I have that var phi x should be 0. Well, this is just a total derivative. It's defined for all x when z is minus h, so of course I can integrate it, and it's a constant. Likewise, at the free surface, my kinematic boundary condition is also a total derivative. That's one of the nice things about looking at it with the stream function formulation. So I can integrate this quantity here along the free surface, and of course I get a different constant. And so these constants of integration we can normalize so that var phi is only determined up to some arbitrary constant. And for a matter of convenience, we pick that constant to be negative n at the bottom and 0 at the free surface. And negative m is defined through this integral.
Okay. So phi is psi minus c.
So yeah, I have to think of this. Phi is psi minus cz. CZ, yeah.
Psi is constant on the free surface. But if you do minus cz, phi is also constant.
There was a vorticity term in the equation that I believe dropped out. That's a good question. Let me go back.
Yeah, there's psi minus cz.
Right.
And that's constant on the
surface. That's a good question.
Is z equals 0?
No, z equals eta on the free surface. That's a good point. I didn't think that through. There must be something that gives rise.
psi is certainly constant, yeah.
Yeah, so let's see. Okay, here.
So
No, this is okay. Let me think about that some more, because if I look at this here, this isn't quite. When I integrate this, right, I'm going to get an extra term here. So in these coordinates, I know most people typically factor out the c originally, and so when you do factor out that c, you end up with these equations directly. And at this point, it's easy to see that you can normalize it to 0. So let me think about that some more and get back to you afterwards. Good question. Okay, so provided that we just move through that, then I can replace these derivatives here with, of course, the constants defined at the appropriate places. Oops.
Maybe I think when you go to a traveling frame, phi picks up
The
an X translation, then psi probably
picks up the z. That's right. That's right. Okay.
Okay, I think that's right. That's
Yeah.
what happens.
I'm so used to the velocity potential formulation
Because you
that
change
they
the
get
frame of
here.
reference, you get this uniform.
Yeah, that's right. Okay, that makes sense. Thank you. Thank you. Okay, so now we would like to determine traveling wave solutions. And again, going back to what my goal is here, I really would just like to solve for the free surface eta. So the equations on the previous slide are, for me, difficult to deal with directly. I would like something that reformulates them, either a boundary integral approach or some other method. And so just like with what Olga was talking about, can we come up with a single equation for traveling waves that solely depends on eta here with the case of constant vorticity? And so if we follow the approach outlined in Ablowitz and Hout, as well as what Vishal and myself used in some other papers, we can achieve this. We can get a single equation. I say single, there's really a family of them, but we can get an equation that solely depends on eta, which we can solve for the free surface. I'm actually going to go through this derivation in detail for traveling waves. I think it ties in nicely with what Professor Filkas has been talking about in terms of his unified transform method. This might be a little bit different approach than what he will discuss tomorrow, but it does give you some ideas about why it can be useful for these sorts of nonlinear problems. So we're going to start with Green's second identity, where for two functions, phi1 and phi2, we can combine them in this way and show that their integral over some domain is just equivalent to the corresponding integral on the boundary of the domain, which involves the normal derivatives pointing outward. Here, since I'm looking at two pi periodic solutions, I'm going to consider my fluid domain, which is bounded below by the bottom of the fluid, above by the free surface, and to the right and left by 0 and 2 pi for 2 pi periodic boundary conditions. And what I'm going to do is I'm going to pick some options for these two functions, and I'm going to look at what happens. So option A, I'm going to let phi1 be my var phi. And I'm going to let phi2 be this exponential, which this exponential is a solution to Laplace's equation. It also satisfies the condition when z is minus h that the normal derivative will be 0 there. Okay, so, wait, that's not right. That's coming up, sorry. It's a solution to Laplace's equation. Let's start there. Okay, so when I plug these two choices into the left-hand side, I can see that this integral over the domain is going to collapse because the Laplacian of phi2 is going to be identically 0. And so this first term cancels out. I'm left with negative phi2 times the Laplacian of phi1. But we know that the Laplacian of phi1, well, that's just going to be negative omega from the fact that phi1 is, of course, var phi, right? That's our Poisson equation. So the left-hand side just collapses to this integral over the domain. The right-hand side, of course, is going to be in terms of these normal derivatives of our choices, subtracted in the appropriate way. So that's option A. We chose var phi and this exponential. Option B, same thing, but now I put a minus sign instead of a plus in front of the kz plus h term. Okay, so I get a very similar equation. The same sort of thing happens on the left-hand side. I get a similar equation on the right-hand side. And so now what I want to do is somehow combine option A and option B together to come up with something that's useful for computation. So from the previous slide, here are two options. Well, now what? Just subtract. If I subtract them, if I look at these two integrals, and we're going to push the integrals together, then this just becomes omega times e to the ikx, and I'll get a sinh from the subtraction of those two terms. And then likewise, I can actually calculate these terms along the edges of my boundary, so that's what we're going to do. We're going to subtract these two integrals, or these two equations from each other, and integrate whatever we can. Okay, so when I subtract, I'm going to get my sinh. And this relationship is only valid for k not equal to 0. I believe Olga mentioned this in her talk. K here will be, for 2 pi periodic solutions, this is just going to be the set of integers minus the origin, or minus 0. And so we have this equation. Let's see what we can do. Focusing just on this left-hand side, well, hey, we can integrate that. It's quite simple to integrate over the domain. So I integrate it, and I get this. I'm left with this one integral that depends on eta, and it's evaluated from x equals 0 to 2 pi. So again, this is just looking at the left-hand side of this equation up top. I evaluated the integral, and now I'm going to replace that term. Okay, so now it's been replaced up here. Now we're going to focus on the second integral down here, the one that lives on the boundary of our domain. And if I think about the shape of my domain, I've got the bottom, I've got the top, I've got the periodic sides. The periodic sides are going to cancel out by periodicity. And so we're just left with the integral at the bottom of the fluid when z is minus h, and the integral at the top when z is eta. So that's what these two components are here. And we have the integral from 0 to 2 pi in x, where we've substituted in z equals eta and z equals minus h. So I can replace this integral along the boundary of my domain with this new integral down here, which exists from 0 to 2 pi over x. One thing to note is this extra term, this first term right here. I say extra, but this term can be evaluated, and because this equation is only valid for k not equal to 0, that integral is identically 0 since k is an integer. So that term drops out, and now we replace the integral up top, and we have this single equation here. Okay, one way to look at this is a Dirichlet-Neumann type map between boundary conditions. I have information about the normal derivative of var phi at the surface being related to these other quantities here. So if I wanted to do an operator expansion, I could find out information about how the normal derivative behaves in terms of eta through this type relationship. And this was explored in Ablowitz and Hout, and Vishal and I have also looked at this in other contexts for 2-dimensional surfaces traveling waves. But this is one calculation you can do. Okay, I'll end with that discussion. So the only thing that's left is if we can write this nicely, maybe we could get a single equation solely for eta that we could solve numerically using some sorts of Newton's method. Well, if we go back to obtain the normal derivative at the surface, we can simply use the following information. The fact that the normal derivative is simply the tangential derivative for the velocity potential formulation, but that's not quite the same here. But what ends up happening is very similar to what Olga was talking about, that you end up with this quadratic equation you can solve once you substitute in the appropriate boundary conditions into the definition of the normal derivative at the surface. You end up with a quadratic you can solve solely in terms of eta. And so we have this square root that we can now plug in to that equation, and everything collapses down to a single integral equation for the free surface eta in terms of the constant vorticity omega. A quick note here, I've introduced this sigma sub s. Sigma is not surface tension here. Although you can include surface tension in this formulation, it would add an additional term here. This sigma sub s has to do with the sign of that square root term. Now, when you take the square root term and you have no vorticity, so if I get rid of the vorticity, I should collapse back down to what Olga showed earlier in her talk. That sign doesn't matter at all. It drops out completely. But here, the sign does make a big difference. And that sign is actually related to the speed at the free surface. So whether or not you choose the positive or negative. So if we go back, oops, apparently I did not put this here, but if we go back to that picture at the beginning where I showed the different shears where you could have one moving negative at the top, one moving positive at the top, and one that has a stagnation point on the inside, the relationship between this and the sign of the vorticity will give you information about how that behaves. Okay. So we can also play this game in infinite depth, and taking the appropriate limits, you can write the equations for constant vorticity as a single integral equation. Here, instead of the cinches, of course, you're going to have absolute values of k's in the appropriate places. Okay, so this is just a summary. So now we have a single integral equation. Maybe we can do the same type of numerics that Olga did to calculate traveling wave solutions, maybe recover the previously known solutions from Peregrine's tape growth that I mentioned earlier. Quick sketch of the numerical methods, just a quick reminder. Olga did a great job explaining this. To solve for the free surface, we will discretize our n's. Apparently k's became n's here. Apologize. That should be little k. So we pick, instead of an infinite number of those k values, we pick some finite set of them going from minus n to plus n. We fix the period to be 2 pi, which is why they're integer values. We, of course, take out the origin from that set. This gives us 2n equations. So those integral equations have to be valid for all integer k's. We've truncated, we've taken out 0, so now we have 2n equations for 2n plus 1 unknowns. And we can think of those as the Fourier coefficients of eta hat. But since eta hat's going to have 0 average, we'll go down in the number of unknowns. So now if I think about the count, I've got 2n equations for 2n unknowns. But I also want to, of course, look at the bifurcation structure, which means I need to fix the amplitude of solutions, and I'm going to vary that. I'll use amplitude as my continuation parameter. And I will need to solve for, let's say capital F. The wave speed C and F are related, of course. So that gives me, if I fix the amplitude, that's one more equation. Of course, for this additional unknown F or C, the wave speed. Use a Newton solver. So I'll pick a good starting guess for a solution. I'll improve upon it using Newton's method. And then, of course, the solution I use there will serve as a way to continue up the bifurcation branch of solutions. And so you repeat and repeat with larger amplitudes, and hopefully you trace out these beautiful bifurcation curves.
Excuse me, before
Yes.
I just get too lost.
Oh, yeah.
Is your C real or complex?
Real valued, yes.
So there's no growing, the wave is not growing in any way.
No. This is purely traveling waves. I'm looking for stationary solutions in a traveling coordinate frame. Yeah, so C is real value. Yes.
Could you say how little c is related to the big F, if at all, on your previous slide?
Yes, so up to a constant, so that constant of integration. Let's see if I can go back. Numerically, what I do is I actually solve for capital F. I apologize. Maybe I went too far back. I should have just used chalk.
Sorry.
No.
There's only one
F is
slide.
big C plus
Yeah.
little c squared.
Oh wait, let's do it this way.
And you fix big C.
Yes, I fix big C, this constant of integration, to be 0. So you can think of this as sort of the up to an arbitrary constant for your stream function that you can determine up to. So let's say we just make that part 0. So now you see the relation between those two.
Thank you, that's correct.
Okay. So let's see if I can go back. Okay. So we repeat and we get up to larger amplitude gases. So in order to start this continuation process, here we're going to bifurcate from trivial flow, so the flat water case, eta equals 0. And of course, as I showed before, we have these various scenarios which depend on the strength of the vorticity. By the way, when you made all these changes of coordinates, really, if you go back to what u was, the horizontal velocity, you'll see that the horizontal velocity has been shifted by this vorticity times z in the vertical directions, which is why these are straight lines for the case of constant vorticity. So that's where those lines are coming from. And so to determine the bifurcation point, so where we're going to find the appropriate f value from which to continue, we're going to linearize around this traveling wave solution of 0 and seek non-trivial solutions. So I plug that into the expansion, or into my single integral equation, turn the crank.
Can I ask a question on
Yes.
the previous slide? I mean,
Absolutely.
those three problems are just the same up to a translation, right? I mean,
In this-
how can they differ?
You'll see that in the behavior of the solution.
The middle one is really different.
The middle one is very different because you'll have stagnation points on the inside. You'll
No,
have
no.
this cat-eye vorticity. This branch, so actually this branch is going to behave very differently from this one as well, because as the stagnation point enters in the fluid domain from the bottom, you're going to get those rounded overhanging waves. You can think of fluid building up as you move the stagnation point upwards.
So, but isn't there, so, okay, so maybe I didn't say it correctly. So,
Mhm.
but it should only depend on C minus U somehow. So it's the relative speed of the C with the U.
But then you
So there's
also,
only one parameter.
you have to think about the sign of vorticity as well. So whether or not the wave is propagating against the current or with the current.
Sure, so C minus U in two branches.
Right, so you get this one for, let's see, against the current. You have
Yeah.
this one for with the current, and this with the stagnation point on the inside.
You see, the problem I'm having here at the moment is that I don't understand, if this flow is not shear, how is the vorticity remains constant?
It is shear.
It is
It is
shear.
shear. It is shear.
This
What
is the shear.
shearing it?
The vorticity itself. So
free
it's in-
floating on a sheet.
Oh, you mean?
Yeah.
It's a recursive problem.
Physically. Well, it's well known that if you start with constant vorticity, then it remains. So that's what she's doing. She just prepares
So
a
it's an
flow.
idealized problem.
Oh,
Yeah, I do.
absolutely.
Oh, sure.
Oh, absolutely. Yes, yes, yes.
Sorry.
I will not argue physicality with you here.
Sorry.
So this was more of a curiosity problem, you know, for myself personally. As I started looking at the bifurcation structure, it struck me as strange. No, no.
In terms of oceanography.
Oh, that's right. Yes, you can complain with constant
It's a more
vorticity.
general problem than the problems that we do with traveling waves. Because we have zero vorticity, she has non-zero vorticity.
All right.
Okay, so,
Yeah, yeah.
okay, let's get back to linearization real quick. We can determine the critical values for F from which a non-trivial solution will bifurcate from the trivial solution by simply linearizing about eta equals 0 and determining the appropriate conditions for a non-zero correction to the 0 solution. You also end up with a dispersion relationship this way, and capital gamma apparently should be a lowercase gamma. It got very excited on this side. Okay, So we can solve the quadratic equation that results from this linearization, and we can find the appropriate values of f, which depend on the sign of the speed at the free surface. Now, one thing I do want to point out here that's a little bit different than other ways people calculate this is that because my integral equation is valid just at the free surface, to solve for traveling wave profiles, it doesn't matter if there's a stagnation point inside the fluid. That never came up here because everything is in terms of surface variables, and so the equation just stops being valid when it should be. And so I don't have to treat stagnation points as separately, just from the perspective of solving for the free surface. If I were to reconstruct pressure or any quantities beneath the free surface using any sort of method, I do have to be careful if I have a stagnation point inside my fluid. So it has to do with quadratics and sign choices and picking the appropriate signs here and there. I'm not going to talk about that here, but I do want to point out that it doesn't matter from the perspective of finding the free surface whether or not there's a stagnation point inside the fluid domain itself.
Sorry, Katie,
Yes.
was capital gamma or little gamma?
Yeah, it should have been a little omega.
Oh, little
Sorry.
omega, okay.
Yes, so I guess little omega grew up to capital gamma. I apologize for that. I tried to make a joke and it wasn't even a good one because it was wrong. Okay, so we know the appropriate wave speeds from which to bifurcate, and we will proceed to find traveling wave solutions by solving our equation numerically using this as an initial guess for the wave speed. Okay, so again, we start from this case. We're bifurcating from here, and we're going to calculate these traveling wave solutions. So I'm going to show some pictures. Let's see how we're doing on time. I might come back to this depending on time. So how to determine if there is a stagnation point in the fluid domain. We'll come back to that if there's time. Okay, so now for pictures. So here, hopefully you can see this. I'm looking at the case for finite depth. Now everything's a bit non-dimensionalized here. So when I say h equals 0.1, that's shallow water. So for me, deep water would be anything above the Benjamin Fear sort of threshold, 1.363. That's how I classify deep water. But here, the depth of the fluid is 0.1. We're looking at waves in increasing nonlinearity as we go down. So the amplitude is increasing, and of course you can see this more spheroidal structure here. And so we're bifurcating, and we're continuing up the branch of solutions where we've chosen the sign at the free surface to be -1, and I believe the vorticity is 0 here. So this is the irrotational case for a comparison. On the right-hand column, you'll see the pressure at the bottom of the fluid. So this was from some other work we have been looking at in terms of pressure, so getting back to the original catalyst here. So now let's look at what happens when we throw in vorticity. Oh, highlight vorticity comes soon. So here, again, I've just taken those same solutions with 0 vorticity. The sign at the free surface has been chosen to be -1. And this, of course, is just the free surface with the streamlines in the top and the pressure contours located in the bottom. So by pressure contours, these are just the lines of constant pressure, the isobars you would see inside the fluid. And the point of highest pressure is denoted here. The pressure actually has a lot to do with why I was interested in stability as well. So there's a reason these are plotted. Let's throw in some vorticity. So you can see how these, oops, wrong button, these become more rounded. They kind of look a little bit more bulbous at the free surface. So this is an amplitude of 0.3. Without showing you the entire bifurcation diagram, it's hard to gauge what's linear and nonlinear, or what's sort of high up the bifurcation branch. When you have large vorticity, by the way, your bifurcation branches, they become much longer. So you can achieve higher and higher amplitudes when you have positive vorticity. And here, the vorticity, for some reason, did not get included in the slide.
Is it gamma?
Gamma equals 1.
Are you restricting yourself to
Second line.
symmetric?
Yeah, that's actually a good question. I am. And that's a really good question. So I'm restricting myself to the symmetric branch because I essentially eliminate all the sign modes from the beginning and I don't solve for those. I think if I included
How
those,
hard would that be to?
you know, I don't think it would be too hard to throw in. The fact is, at the bottom of the branch, you're just going to end up with the cosine modes. And so the only time I think, and I might be wrong with this statement, but my intuition seems to say that as I go higher and higher up the branch, that's where I'd probably see the sine modes come in. So why solve for them when I don't need them? But that's an interesting question. I think most non-symmetric traveling wave solutions I know bifurcate from higher up a branch, but I'm willing to take any corrections on that understanding. I'm not 100% certain. Okay. So, oh, there, gamma. Sorry, that should be omega. Here's the interesting part for me, which is I start going up the branch, and all of a sudden, I introduce a stagnation point in my fluid, and it enters, in this case, from the bottom of the fluid domain. So when I drew those pictures earlier, where I showed you the fluid domain and the intersection beneath the fluid domain, this is a case where the stagnation point entered through the bottom. And as the stagnation point enters through the bottom, you get these cat-eye vorticities, or vortexes here. So you can see the fluid motion changes quite a bit. You get this more bulbous shape. And the interesting thing here is the pressure. So if I look at this contour, this is very similar to what Peregrine has seen, and some other people have seen in sort of KDV-like models, which is the pressure is actually 0 on the free surface, as we prescribed. It's also 0 underneath the free surface. This region here, that's colored in light gray, is actually a region of lower pressure. And so you can imagine that there would be some type of instability that could potentially arise as this sort of behavior happens. And so this is sort of the things that got me motivated into looking at what happens in stability. Yeah?
Why doesn't that bubble collapse if it's lower pressure?
That's a good question. I assume the shear is somehow stabilizing it, or
It's a Kelvin schizoid.
it's a. So that's the cat's eye here.
No, and then the bottom picture is what I mean.
This, yeah. So this is the streamlines. This is pressure, and that is interesting.
Is that,
Well,
is
it's
that
a
pressure
vortex,
the same
right?
sign? Is it positive or negative?
I'm
It's a
sorry, is that-
vortex.
It's negative.
And the
This
vortex
is
low
negative.
pressure in the center.
This is positive pressure, negative pressure inside
It's a
here.
cavitation.
Yeah.
Yeah, it's just like.
It's incompressible vortex.
Yeah. Okay.
These are words I use, so incompressible vortex. Okay. Okay, so this is, again, sort of what got me interested here, is, you know, what's going on in terms of stability for waves like this. Are there certain perturbations that are going to split this apart? What's going to happen? Are you going to have the sort of finger instabilities that you see in other fluids? I honestly don't know, so I was curious. I'm not going to have an answer for you on that today, by the way, so I don't want to get anyone excited. Maybe someone already has an answer, though. I'd love to hear it. Let's look at a case now where the stagnation point begins for the trivial flow above the fluid domain. And so as you continue up the branch, the stagnation point actually moves closer and closer to the free surface. You get more crest-like behaviors that you see in plane gravity waves. And this is why I like to draw that picture just for myself. If the stagnation point enters from the bottom of the fluid, you get the rounded overhanging type waves. If it enters from the top of the fluid, you're going to get a crest and a limiting wave that has a peak. Now, I haven't been able to go high up the branch at this point because really what I want to do is change my coordinates from x to something that's parameterized along the free surface so that I can do overhanging waves as well as, you know, things that need to be resolved more accurately. And you can do that within this integral formulation. So that's one nice thing. Going to higher dimensions, I'm not going to make any speculation about that, though. But at least for the two-dimensional fluid, one-dimensional surface, you can, in theory, do overhanging waves. And I believe I have some preliminary calculations or work, but we're not there. Okay. So I keep coming back to this picture. This was just to remind you, in this case, as the stagnation point moves up, we get the overhanging bulbous type waves. Here, as the stagnation point moves down, you're going to get the crest. And so this situation, right, the stagnation point can maybe move up and down I'm not quite sure how that's going to depend. Again, more things to investigate. Going high up the branch is exciting, but I found that lower on the branch, there's some really bizarre things that happen as well. So here's a curve. Q is the same as F. Apparently I've gone through many, many different phases. One day I'll settle in on the appropriate variables. So think of this as your wave speed or your nearly constant F. Think of this here, of course, as, well, it is the maximum value of the free surface. I'm limiting this pretty small for this large of vorticity, so 3. As I go up the branch, the solutions don't seem to change that much. So again, going up this branch, I believe this solution here corresponds to the top, and this solution corresponds to the bottom one. They don't really look that different from each other.
But the magnitude is different.
The magnitude is very different. You're absolutely right. I want to point out that, again, positive vorticity, h equals 2. My bifurcation curve bends to the right. Right, okay. Vorticity is 3, h equals 1. Bifurcation curve bends to the left. Completely different. I didn't expect that. I was kind of curious. Well, if it goes from bending to the right to bending to the left, obviously you want to figure out what happens in between. Where does it switch? Is it continuously dependent? If I take h going up from 1 to 2, when does it switch points?
Is gamma the same as omega?
Yes, I'm sorry. Yes, gamma is the same as omega. Here, that's just my vorticity parameter.
And Q is C, which is F.
Yes.
Yeah.
Yes. I should have put legend here on the board. I apologize for that. Maybe I should pass out flyers, or maybe it's a quiz at the end, but I apologize for that.
Is this postscript? Then I can fix it for you.
I know. You know, that would have been a smart way to do it. But no, unfortunately, it's
You
not.
haven't been a student of Julian Hunt, isn't it?
What was it?
You haven't been a student of Julian Hunt, have you?
Nope.
From one page to the other, the same notation changes many times. They don't mean the same thing. You'll probably see that tomorrow.
Well, at least you'll have a warm-up for it, right? So I do my part. Okay, so again, looking at this, and the bifurcation curve goes to the left. So what happens in between? So let's look at different h values. Apparently this is the same. As I dial h in between 1 and 2, what I find is that that curve, that nice smooth sort of square root or you know, parabolic type behavior flattens up. And I have no idea what's going on here.
That's what you expect, isn't it?
Well, you would expect that, right? But as I dialed in more and more, it just became more and more vertical, and that would be
It has
something.
to go from.
Yeah, and that would be something you'd think you could show
Oh, yeah,
analytically.
yeah, right, yeah.
And I haven't been able to get to that, but this numerics is really interesting to me in the sense that how exactly does that structure change, and how can I numerically compute this? And this is for really small amplitude. This is at the bottom of the branch.
So what is the physical significance of that value? Is it a large value vorticity, a small value?
So I would say that omega equals 3 is a larger value of vorticity.
Is it dimensionless?
That's a question I need to figure out. It is dimensionless here, but I'm not sure what the appropriate, I'm not sure if I'm using the right non-dimensional parameter. So I'll kind of hint on that at the end. Yeah.
Do you get the same switchover value of h regardless of omega?
No.
Get different ones for different omegas?
Yes. And so this got me even more thinking about stability. What exactly is going on here? And I mean, it's not exactly the Benjamin if you're cut off, but it
Omega
feels.
is 0, it's 1.36,
It,
etc.
it feels, yeah, it feels a lot like that. So does this have connections to loss of Benjamin fear instability? So all of these sorts of things, you know, seem to be tying me back into instabilities, and it should, right? If we think about bifurcation structures, turning points, things like that.
There is an extra instability because of the, you know, basically if I see it as an oceanograph, so I see this current,
Mm-hmm.
then you have waves that are traveling faster than the current at the surface and waves that are slower. The waves that are faster are, say, prone to Benjamin fear instability, but the slower ones, they will get energy from the shear and start growing. I mean, that was
Interesting.
Blocking,
obtained.
right?
No, that was I wouldn't say blocking, it was obtained by Safman and Ewan in
Mhm.
87, 88 or so.
That should be something I definitely look
Yeah,
at.
so
yeah.
I would expect that, and
Yeah, this
Yeah.
is something I definitely should look into. I'll ask you more
Yeah.
information about references later. So again, this was puzzling to me. So I want to look at the stability here. In other cases, this is relatively small. I mean, okay, I shouldn't say relatively. This is incredibly small amplitude, and very low on the bifurcation branch. You're seeing already the sort of interesting turning point. So this is something I want to investigate a bit more and see what I can say analytically about this, because again, for it to be such small amplitude, for this to happen there, you would think that you should be able to get at it with some sort of perturbation scheme at very low orders, and unfortunately I haven't been able to.
What if instead of using max height, you use some energy measure?
That's a really good point. I should probably do that as well. Look at all the sorts of quantities. You're right.
but really, you just want to do linear theory.
Yes.
But
Okay.
so Safman.
Yeah, I will definitely take a look at that. I mean, to the best of my knowledge, the only stability results I know have been relatively recent in terms of nonlinear Schrodinger type models, where they were able to derive it there and show the Benjamin Fear instability does change as you change the.
He did it for the same equations as you.
Yeah, I will definitely be talking to you about that.
What is the horizontal scale? Like, all of the values seem to be the same.
I'm sorry. What?
What is the horizontal scale?
See, this is the wave speed.
Yeah, but
C.
10 to minus 3.
I think you're right.
Oh, yes.
Digit changes.
No, it should be. It definitely, it's much smaller. So I think maybe.
This is a straight line.
Yeah, it's pretty much a straight line. But for there to be such smooth structure, there's a warning at the end of my slide, or at the end of my talk, where I say I should heed Olga's warnings and be very careful about my numerics. But there is something peculiar going on that I want to learn a little bit more about. But maybe it's already been done.
Epsilon to the fourth here would be 10 to minus 12. So if C2 is 0, then C4 is non-zero, then you would get this.
Okay. Yeah, I need to think about this a little more. Yeah, he's talking about the, basically the expansion corrections. Yeah. Yeah, let's talk about this as well later. I'm running out of time, and I want you to have at least a moment to stand up and stretch your legs before the next talk. So what about stability? I'm going to just run through the derivation. Basically the same idea as that of Olga. You can find a time-dependent equation. You can, Ashton and Focus have a time-dependent version of the problem with constant vorticity. So of course we linearize around one of these traveling wave solutions, and of course we end up with an eigenvalue problem we saw for lambda, and we see what lambda looks like in the complex plane if lambda has a positive real part in stability. Okay, so I'm going to skip this for the sake of time. Okay, here's what Olga showed for deep water with no vorticity, and this is the zoomed in version where you see at the origin the sort of classical Benjamin Fear instability. This corresponds to long wave perturbations. There are also those bubbles way up there and way down there, but we're focusing for this part just solely on Benjamin Fear. Okay, so again, positive real part corresponds to instability. And as Olga showed, if we of course look at our changing the depth h, just as I was mentioning before, as I changed h, the bifurcation curve switched sides. Well, for no vorticity, right, as we change h, we end up with instabilities due to long wave perturbations. So I'm only showing long wave perturbations on this slide. We can of course do other scales as well. So I'm going to focus solely on infinite depth because things are easier there. And if we lose Benjamin Fear in infinite depth, then we should expect that it's going to be affected in finite depth. And so this is where I'll end on these few slides. Let me describe what you're looking at here because it's a very different plot. On the horizontal axis, you can think of this as a measure of the perturbation that I'm putting in on my system. So on the horizontal axis near 0, you're looking at long wave perturbation. So this is my flow k parameter, and as mu, my flow K parameter is closer to 0, I'm looking at long, 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 long wave perturbations. Unfortunately, you can't see the scale, but that is 10 to the minus third. So these are all long wave perturbations. On the vertical axis, you're looking at the maximum of the real part corresponding to those long wave perturbations. So whenever you see a curve, that's an instability. For no vorticity, for omega slash gamma equals 0, you see your classical Benjamin-Fehr instability here. As I increase the vorticity, it splits off away from the origin. And the magnitudes are actually relatively similar. We'll look at them in comparison in a second. As I go in the opposite direction, so as the vorticity switches, or another way to think about this is your wave is traveling in the opposite direction. Same strength of the vorticity, I see a very different structure. Now these scales here are really strange. Yeah.
There is something physically wrong with constant vorticity in water of infinite depth. So if you just think about flat waves, the kind of shear velocity will go to infinity. So it's completely unphysical.
Oh yeah,
Probably,
yeah.
let's say.
You have to do it like this.
No, you're.
It goes to infinity.
No, but I mean, you have to do it like this. That's all.
Yeah.
I mean, you can think of it as an approximation.
Yeah.
Like
Yeah,
finite
no.
not much.
Yeah, you're absolutely
The wave
right.
goes down, so yeah.
Yeah.
I mean,
No.
you can take a limit, h large,
Mhm.
and see how that
Yeah.
picture changes.
Yes, and you're absolutely right. I mean, there is a lot wrong with this. So this is the starting point, and then of course, based on what you see here, maybe we should go back and look at finite depth more carefully. So it's completely valid criticism.
Or short wavelength compared to that.
Oh yeah.
Yeah.
Here's something interesting though. I increase the vorticity a bit more in the negative direction, so I go negative vorticity, and it's all gone out of this picture. And so again, there's something strange going on here. I still haven't been able to describe the flipping in terms of stability, but you know, at least maybe we can say something about Benjamin-Fehr in relation to bifurcation branch structure through this sort of picture. Yeah.
Have you compared to this paper of Karif?
So
where
this
he
is
does the NLS model
NLS.
for this?
This is actually something I'm looking into. So I believe this was 2012, coastal dynamics. Yeah. Yeah. So I do know that the directions and the signs and sort of the general conclusions are consistent. Whether or not the scales or the rates, I haven't been able to compare that yet, but it's definitely
I
on
mean,
my
given
list.
your amplitudes, this should be approximated by NLS, right?
Oh,
problem,
yes,
so-
yes.
Yeah, to a degree, yeah.
And they do find this sort of change in the Benjamin-Fehr instability within the NLS model. So as you tweak the coefficients appropriately, it changes. Okay. So here, again, I want to leave with the last few pretty pictures. I'm showing it in the complex plane. So again, positive values, positive real values correspond to instabilities. On the right-hand side, you're looking at the flow K parameter. So this tells you how long the perturbations are and the instability, or where the instabilities occur with respect to long wave perturbations. I compare it with the irrotational case in blue. You see positive vorticity, you see negative vorticity. I think the signs might be wrong. Let's see. This should split away for positive vorticity. They're switched. It's been I don't know what I can blame it on, just lack of care.
So
I
blue,
apologize.
so green, and red.
Yes, and which are probably not the best colors to put on a slide anyway. So I apologize for that too. Lots of apologies here today. But the point I do want to show with this is you can see relatively that the magnitudes of the instabilities in these cases don't seem to change that much compared to each other, but the overall place or location of the instabilities or the types of long waves that give rise to instabilities does seem to change, and we can increase the vorticity more, and we can see how this continuously deforms, and the red collapsed down to the real axis, here, or collapsed down to the real line, and these bubbles have now shot off in the complex plane.
But they originated from the origin.
They originated from the origin, that's right. So just following them back, you can see. And that red curve does more smoothly collapse back down. I should put a slide in there. So that's pretty much it. Future directions, also known as an appeal for help or collaboration. A couple things that I want to do with numerics is, of course, make sure that this is not sensitive to round off errors or things like that. I want to really make sure these numerics are right, because those scales of gamma that I was showing you, that was 10 to the minus 7th. Something makes me feel like the non-dimensionalization I'm using is a bit off. So I want to think about that more carefully and make sure my numerics are right. Also, understanding the Hamiltonian structure for this problem. It seems like there's a little bit of debate if this is Hamiltonian or near Hamiltonian. I think it depends on what you define as acceptable for your Hamiltonian. So understanding Moline structure for the Hamiltonian here and incorporating that into the numerics, I think would be very helpful, especially in terms of prime signatures, things like that. Calculating the instabilities for a broader range of perturbations. All I showed you here was long wave. In theory, all flow K parameters should work, but this is something I want to figure out a bit more. And I will just, and you can see, compare with the recent results for NLS models, so digging more into their results. And I believe there's also 1 or 2 new papers on the archives as of like a couple weeks ago as well. So constant vorticity, I guess, seems to be attracting a bit of attention. But with that, I'll end. Thank you.
Is it vertical vortex, constant vertical vortex?
No, this is
Yeah.
pointing out of the board.
Yeah, it's coming out of the board. So
Do you, like you said,
Yeah.
think of the rotation.
No, because the French actually produced a paper. It's
It's
actually,
yeah.
no, this is great, but as they produced a paper, it's absolutely astonishing. It's a variational principle of collapse transformation with a constant vorticity.
Yes,
Now, you've seen that, have you?
I know about it.
Absolutely, you know, I mean, the things, they always said, if you could write the variational principle for water waves with vorticity, there's a lot you can get at them.
It's actually in Luke's original paper.
Oh,
Yes,
yeah.
yes.
He has Klebs variables in the original paper.
Yeah, but it doesn't have vorticity.
Well, that's what Klebs variables are for.
Yeah, that's the reason why you use Klebs.
Yeah, but he doesn't have,
No.
doesn't have.
Yeah, but I mean, we know the Hamiltonian in presence of vorticity.
Oh.
But one of Sathman's students looked at a simple case of constant vorticity and adding that to Luke's